Hi there, you're in the lab with your mate JJ. Today is Learning the Art of Electronics Day. Today we're going to be learning the art of electronics. My silly job title for today is Electron Enchanter. Today I'm the Electron Enchanter. And of course, the Learning the Art of Electronics is our hands-on lab course that we're working through. Today we're going to start on the second chapter. We're working our way through the first section on DC circuits, and we've already covered all of the notes. So that chapter is done, and I completed that with you last week. So today we are going to start the lab part of the DC circuits chapter, section, whatever you want to call it. So what we'll be doing actually is popping over to the bench to do an experiment with the burden voltage, and we'll explain that over on the lab when we get there in a second. After that's done, we'll pop over to the computer and do the theory part for the week. There won't be much there, but just a few notes. We're starting to do the notes for this lab, and that will continue. So we're not going to finish the lab today. We're just going to start it. We're going to do one experiment with the burden voltage, and then we're going to review the notes, and then we'll pick it up again next week. So first things first, let's pop over to the bench and have a look at the burden voltage. All right, well, here we are on the bench, and this is our book, and today we'll be working through section 1L.2.2.1, an experiment. Try your DVM's current measurement burden. Just how low is the voltage that the DVM measures when it's purporting to measure current? With your DVM set to measure current, let's call this DVM A, tie a 1K resistor to plus 5 volts as we just suggested, and use a second DVM, B, to measure the voltage between the two leads of DVM A, which is measuring current. This voltage is the one called the meter's burden on the circuit. We hope the value is a small fraction of 5 volts, since it tends to distort the current relative to what it would have been absent the current measuring meter. See if the burden changes if you replace the 1kR tied to 5 volts with a 1 mega ohm resistor. Okay, cool. So 1 second. All right, so we're going to start setting up DVM A, which in this case I'll just make the fluke here. So let's take positive power in can come through from here. So that's just the power supply at the back here. I'll turn it on in a minute. So that power is coming here, and then it's going to go in here, and we'll send it through a resistor, and I've got one of those over here. Let's just make sure they're all off. We don't want to turn it on while they're all off because that'll short circuit. And then we'll send the power in over here, and then we'll complete the circuit by sending the rest of it back over to the power supply. I'll just show you that. So that's here. Now I'm just going to power up the power supply. So it should power on. Here it comes. There it goes. All right. Now we haven't got it turned on at the moment, and that's good because it's set at 0. So let me just throw you back over here, and we're going to set this at 1K. So we'll pull that in, and we've got 1K set on our resistor coming through the meter. So let's put the meter into milliamp mode. I don't know if milliamp or microamp will be required, but we'll know soon enough. See how we go with that. Can you see that? Not really. No, I'm going to leave it this way for you. There you go. You can see that. All right, very good. So let's throw you back over here, and we'll V set at 5 volts. and it's over current at 1 amp, which is heaps. It's on continuous voltage, which is what we want. So let's see if we turn him on, if he blows up or not. Okay. So I was expecting to see something here, but it's not showing me anything. What about if we put it in microamp mode? That's nothing. How is that nothing? I'm quite surprised about that. It says 1K here. Oh, there we go. It's getting a reading now. Overload, milliamps, 4.99 milliamps. All right. We might just also plug in this guy, put him on small milliamps, and we'll just clip him on over here and see if it picks up anything. It says 2. Okay. So it's 10, 20. So it doesn't have a very good rating, but this gives us a pretty good rating. It's reading 4.97 DC milliamps. Very good. Now what we're going to do is measure the voltage across this resistor here on our second DVM, which is the good old trusty EV blog BM2257. So we're going to be measuring voltage. So let's put this guy in voltage mode. There we go. That's DC voltage. Very good. So let's put this here and here, and look at that. It's measuring. It's measuring 4995. Oh, okay, of course. So, okay. Okay. I'll just be back in just a second. All right, I'm back. And of course, what I did then was the wrong thing. I put the voltmeter across the resistor, but we don't want to measure the voltage drop across the resistor. We want to see what the burden voltage is, which is what appears here across the leads of the DVM-A. It is quite odd that the milliamps and the voltage is so close to each other. But of course, these are milliamps, and the power is volts. Anyway, the answer is 0.006 volts are being used for the burden voltage. Now, what I'm going to do is I'm going to throw in a 1 meg resistance. Okay, and then the voltage has gone so low that we can't actually see it anymore. Yep, the voltage is so low that we can't get a reading on it on this meter. You know what we might do is try reversing them. Just oh no, we'll do it together. I'll just turn that off, and we'll take this guy out, and we'll put this guy in current sensing mode, and we'll put him in milliamp mode, and then we'll plug this guy in here to be the voltage measurement. We'll put him over there on millivolts. So now we're going to run the current through the blue meter and pick it up on the yellow meter, and we can get that out of the way. We don't care about that. All right, so let's throw the power onto this thing and see what happens. We're up at 1.1 meg or something like that. Okay, on we go. All right, what are we looking at? Something's wrong. Maybe if we put it into microamp mode. Yeah, there you go. All right. So it's 5 microamps and 4 millivolts. There you go. So if we take that out again, all right, so it's gone up to 4,000 microamps, and it's overloaded this. So the burden voltage is 0.5 millivolts when we use the 1 meg resistor, but we had to switch them around. The fluke is obviously oh no, there we go, there is millivolts on this meter. It's got voltage here and millivolts over there. So let's put it back how it was. Put him back on multi, and we'll put this guy on milliamps, microamps. No, that's not right. Is it? Oh yeah, it is. Yeah. Okay, cool. I think it is. All right, let's throw the power on. All right. So that's using, again, 0.5, very similar, 0.5 millivolts. It's half a millivolt. Yeah, cool. All right. Actually, I should have made some notes. I'll have a break and we'll come back and we'll make some notes. All right, so what we'll do is we'll make some notes about our results. So today is the 4th of November 2025. Of course, I'm Australian, so I put the day first. And this is LAOE. Get the section number out of the book here. 1L.2.2.1. 1L.2.2.1. Now what we're going to have is the resistor. So we'll have R, and we'll have V burden. So let's say at 1K, let's put this in 1K and turn him on. So we're measuring 1K. And we're using 732 millivolts. 7.32 millivolts. And we'll do 10K. So we'll put him in 10K. And we've got 0.73 millivolts. And then we'll do 100K. I'm putting in 100K. And we've got 0.067, says 7 now. And then we've got 1 meg. So we'll put in 1 meg. And this is millivolts. It's not showing anything. And the current is actually, you know, we could put the current in there as well. Oh, that's interesting. All right. So if we changed that, it affected this. Yeah, right. Fascinating. So the burden voltage goes higher when we try to measure smaller current. That's a bit unintuitive, I find. That's odd. Anyway, that's what we've got. So, yeah, right. Okay. I'm going to get a drink and I'll be back. All right, I'm back. I had an orange juice and an apple. Now, I think what we're going to do here is we're going to do two sets of measurements. We'll do measurements with the microamp and measurements with the milliamp. Let's put that on milliamp mode. Put this guy back on 1K. All right. So I'm going to call this IM, and then we're going to rule it off here, and then we're going to go again R and V burden, and this will be I micro, I mu. So let's say this is 4.9 milliamps, 4.98 milliamps, and then we'll pop this up to 10K, and it's 0.72 or 73, that'll do, and 0.49 milliamps, and then up to 100K, and that'll be, it says 0.5 there now, but we've got 0.7 written down. What are we going to do? Might as well adjust it. Same with this one too, I guess. So that was 2, and this is 5, and this is 0.04 milliamps. And then if we bump it up to 1 meg, then this says 0.00 millivolts, and this says 0.00 milliamps. Okay, now we're going to kick off over here. We're going to do 1K. Sorry, I made a mess of that. 1K, 10K, 100K, 1 meg. All right, so we're going to put this onto microamps, and we're going to put this in 1K, and the burden voltage is 4. Oh, that's okay. That's let me change that. So it's at 1K, and the voltage is 4.9 millivolts, and the current is OL. And then if we bump him up to 10K, then we've got 49.78 millivolts, and the current is 497. It's dyslexic John. 497 microamps. And then we'll bump him up to 100K, and we've got 0.5. Oh no, that's 0.5. We've got 0.5.01 millivolts, and the current is 50.1 microamps. And then we bump it up to 1 meg, and the burden voltage is 0.50 millivolts, and the current is 4.9 microamps. Okay, now I'm going to turn this off because we're done with the experimenting. I'll take these out. All right. All right, cables everywhere. Oh, yeah. All right. So let's have a look at our results together. What have we got? So when we were measuring the current in milliamps, it used different burden voltages. So when we were measuring, yeah, right. So the burden voltage was higher for the microamp readings. Wow. And the higher the resistance, the lower the burden voltage. Yeah, interesting. There you go. Anyway, that's what we learned. We learned that you increase the resistance of the load and you decrease the burden voltage. Similarly, if you change the scale, you you blow up the burden voltage. Oh, it's quite interesting. Anyway, the next step is to jump over the computer and do the theory part of the course. So we'll do that now. All right. So here we are on the computer, and what we're going to be doing is going through the notes for the chapter. Now we've started a new chapter. Last week we finished 1N DC circuits, and this week we're going to pick up 1L, which is the lab. So we're getting ready to do the lab. We're not actually doing the lab today, but there is an exercise in there. So if you want to do the reading for today, then read up to page 28 from the coursework. That's what we'll be doing today. So I'm just going to open up this chapter. And I'm actually moving these chapters out into a sub page. Just waiting for this to load here. So as you can see, on the learning the Art of Electronics second edition page, which is this page, we link through to the whole chapter, and that gets its whole own page. And this is just a fresh start that we're doing today. So this is the theory and the results from the experiment that we did today, up to page 28 in the book. So this is 1L lab DC circuits. So this is Ohm's law. This lab is to get you used to the breadboard and the multimeters. We don't expect you to find Ohm's law surprising. So it's really just an excuse to take the breadboard and the multimeters for a spin. They encourage you to build your circuit on the breadboard and not in the air. So just try and put everything on the breadboard and don't use alligator clips and gravity and air. You use solid core AWG22 wire to interconnect components on the breadboard, and you want to strip 3/8 of an inch or 0.375 inches or 9 millimeters of insulation off each end. Be careful not to apply power to power outputs which might be present on your breadboard. They use a particular trainer board for their courses. I had a look at them actually. They're about $1,500 each, so I'm not going to be getting one of those. But some of them do have power, so you want to be careful that you don't plug power into power. And the standard colors that they use for their voltage carrying wires are red for 5 volts, yellow for 15 volts, and blue for minus 15 volts. We've got a note here that voltages are measured between points on a circuit, whereas currents are measured through a point in a circuit. This means you usually have to break a circuit or interrupt the circuit in order to measure current. And there's a link here to the to hints and tips on using the breadboard. So if you're new to breadboarding, certainly check this out. This is chapter 1 online content. So by all means, check that out. We might have a quick look at it ourselves. Why not, huh? This is chapter IO online content. It's available for free from the website, so just follow that link that I showed you there. We've got solderless breadboards is what we're willing with. 2 possible breadboard choices. So this is just how the wires behind the breadboards work. An optional analog only breadboard. So this is the other type of breadboard they have in their lab. Did they give us a photo of the big one that they use? Oh yeah, okay, this is still the same one. Here it is. And this is the top right here. This is power. So you don't want to go plugging power into that. That's power output there. And they just give you some tutoring, tutelage about how to use the wires. So as you can see, there's 9 mils of insulation removed. You put the integrated circuits across the little trench that's in the middle of the breadboard. What do they say here? Do not daisy chain jumpers unless there is a device connected at the junction. Do not change wire colors in a daisy chain. Okay, fair enough. So this is an example of a neatly built circuit. Very good. Additional breadboarding hints and tips. When you disassemble a circuit, do not try to remove ICs by hand. You will bend the leads. The U-shaped IC extractor should always be your first choice. Very good. Use your pliers to fix the legs if you need to. Okay. So even if you decide not to memorize the resistor color code right away, keep these rules in mind. A resistor starting with brown then black is an order of magnitude value. A brown third band means hundreds of ohms. A brown, black, brown equals 100 ohms. Anyway, there's a bunch of details there for you. It's pretty comprehensive, really, about how to use the scope and everything. Right. Wow. It did take me hours to read all this out to you, but if you're interested, it's available. It's 26 pages. So this is the next chapter that we're up to, the meters and the VOM and the DVM. So in this course, analog meters are known as VOM, short for volt, ohm, milliammeter. And these devices are fundamentally current measuring devices, which can be tricked into measuring voltage. Whereas the digital meters, known as DVM, short for digital voltmeter, fundamentally voltage measuring device that can be tricked into measuring current. And that's what today's experiment is. To measure current, a DVM runs the input current through a small valued resistor and measures the voltage drop across the resistor. A particular resistor value is picked to keep the resulting voltage under a volt and much lower than that for some ranges. The small voltage and that the DVM drops when measuring current is called the burden voltage. Ideally, it would be 0 volts so as not to alter the current from what it would have been absent the meter. A side effect of the fact that the DVM is a voltage measuring device is the need to switch input leads when measuring current. If you forget to switch the leads, you might blow the fuse. There's a note here about the Keysight U1240 datasheet regarding burden voltage, if you want to check that out. Here's the experiment. Try your DVM's current measurement burden. So just how is the voltage that the DVM measures? How low? Just how low is the voltage that the DVM measures when it is measuring current? We connect DVM A to measure current through a 1K resistor with a 5 volt supply, and we connect DVM B to measure voltage across the leads of DVM A. This voltage is known as the burden voltage. So we did this experiment twice. In the first case, we set DVM A to measure milliamps, and in the second case we set DVM A to measure microamps. The particular current setting affected the results. So the burden voltage is different depending on which mode you've got the DVM in. So with the DVM A set at milliamp range, the V burden from DVM A is measured from DVM B. So when we put in 1K, the burden was 7 millivolts. When we put in 10K, the burden was 0.7 millivolts. We put in 100K, the burden was 0.05 millivolts. And when we put in 1 meg, it said 0. It couldn't handle that resolution. So we did the results again, and we lowered the voltage range, the ammeter range from milliamps to microamps, and then we measured again. So when we measured 1K for microamps, it was overload, so the value was too big to be displayed, and then 10K. The burden voltage dropped down by an order of magnitude, and we got a reading here, 497 microamps. So you can see that the voltage has gone way up, but the current has gone way down. And then we've got 100K, and it had 5 millivolts burden, and it measured 50 microamps. And when we put it in 1 meg ohms, the burden was half a millivolt, and the IA is the current. Yeah. All right. So I think that's everything. I'm going to throw you over to the farewell cam. We'll wrap up. Actually, just before I wrap up, I want to be clear, because it confused me a little bit, because the units have changed from milliamps to microamps, but actually the values have stayed the same, and that's what you'd expect, because the current is set by the resistor, the 1K resistor, and the 5-volt supply. So that dictates the current, and that doesn't change between the circuits. So I was expecting these to be the same, and they are indeed the same, but it was just a bit confusing for me, because these are in microamps and these are in milliamps, but actually 4.98 milliamps is OL. It's too big for a microamp reading. So and the 0.49 milliamps is the same as 497 microamps. It's just, if you were gonna write this in microamps, that's basically what you do. So we actually see that the currents are pretty much the same, just with some precision issues there. But it is basically what we'd expect to see, that the current is the same in both cases, and the burden voltage is the thing that changes. So yes, with that, I'll take you over to the farewell cam. We'll wrap up. And that's a wrap. So what did we learn today? We learned about the burden voltage on a digital voltmeter. So we did two sets of experiments. One with our DVM set to measure in the milliamps range, and again to measure in the microamps range. And we found that the current through the circuit stayed the same, but the burden voltage varied, and there was a higher burden voltage for the lower resolution current, which is perhaps odd, I'm not sure, but I think that's what we saw. So I think that concludes this video. I hope you enjoyed this video. Thanks very much for watching, and please remember to hit like and subscribe.